Now discussing some more questions on computing for medicine. So a researcher wants to test whether blood pressure significantly decreases after taking a new drug. The same patients are measured before and after treatment. Which test should be used? We should use paired t-test. Now a 95% confidence interval for the difference between two populations means mu1 minus mu2 is calculated to be minus 0.5 to plus 1.5, which suggests that the null hypothesis h0 is equal to 0 cannot be rejected at the alpha is equal to 0.05 level as the interval contains 0. Now, the CLT, that is central limit theorem, states that for a sufficiently large sample size, the sampling distribution of the sample mean will approach a normal distribution regardless of the population's original distribution. PCA reduces dimensionality by keeping components with the highest variance. Now, a fair coin is tossed 3 times. Let the random variable x denote the number of heads obtained. Which of the following represents correct probability distribution of x? The answer is x is equal to 0, 1 by 8, x is equal to 1, 3 by 8, x is equal to 2, 3 by 8, and x is equal to 3, 1 by 8. Now, two researchers work with highly skewed data. Researcher A uses raw data in hypothesis tests, and researcher B uses a sample means with sample size n is equal to 50. So, which conclusion is justified? Only researcher B can use normal approximations because it uses sample size n greater than equal to 30. Greater than 30. So, we use a normal approximation for this one, not for researcher A. Which property is essential for an AI system to be considered agentic? That is autonomy. Now, increasing the lasso penalty parameter lambda will reduce the number of non-zero coefficients. A research paper claims that an agentic AI can alter its own reward function to optimize performance over time. So, which potential issues does this highlight? So, autonomous goal modification leading to unintended or unsafe behavior. When is lasso regression particularly useful? When we have many correlated features and want to perform variable selection automatically. Now, which statement about TSNE is true? So, TSNE is stochastic. Results may vary across runs and depend on perplexity. Now, suppose a rare disease occurs in 1 in 1,000 people. A test has 99% sensitivity and 95% specificity. Using Bayes' theorem, the probability that a person testing positive actually has the disease is close to 0.02. Right? Which of the following correctly distinguishes population versus sample variance? So, population variance divides by n, sample variance divides by n minus 1. Now, a researcher is studying the prevalence of genetic mutation in a population. They estimate that the probability of an individual having mutation is 0.05. If two individuals are randomly selected from the population, what's the probability that at least one of them has the mutation? Assume presence of mutation in one individual does not affect the probability in another. So, answer is this. We will be discussing the concept behind this in another video, but let's move on now. When visualizing clusters with TSNE, why should results be interpreted cautiously? Because clusters may appear well separated even if the original data does not have clear separations. Now, what are the different methods of dimensionality reduction and explain how PCA reduces dimensionality while retaining the most important features or information in data, and how is trade-off between variance retained and number of components decided. Discuss limitations of PCA as well. So methods for dimensionality reduction can be TSNE, PCA, autoencoders, UMAP, right, and LDA. So how PCA reduces dimensionality? First, we compute the covariance matrix of data, find eigenvectors, that is principal components, project data onto components with highest variance, and keep directions capturing the maximum variability. These are the principal components. Trade-off is decide the number of components using a screen plot or cumulative variance. Example, keep enough components to retain 95% of variance. So keeping more components means higher variance is retained. So more principal components leads to more information being preserved, better reconstruction of original data, and less loss of signal. But it also leads to higher computational cost, harder to visualize, and risk of keeping noise. Now, keeping fewer components leads to lower dimensionality. It leads to a simpler model, faster computation, easier visualization, helps reduce overfitting. But it loses some variance information, potentially loses important patterns, and may distort relationships between the variables. Now, how the trade-off is decided? So, cumulative variance threshold. We choose the smallest number of components that explain. 90% variance is common, 95% variance is strict, and 99% variance is for higher precision tasks. For example, if the first three principal components explain 92% of variance, we keep them. Now, limitations of PCA, it assumes linear relationships in data. It is sensitive to outliers. It is sensitive to scaling of features, cannot capture non-linear structure. Components can be difficult to interpret. Now, a diagram of PCA you can draw, and you can see on the web itself. Now, how does is our second question is how does Bayes' rule assist doctors in making accurate medical diagnosis when the same symptom can be caused by multiple different diseases? In your answer, explain how prior probability, likelihood, and posterior probability are used, and give an example of how Bayes' rule can help differentiate between two diseases and that share a common symptom. So examples can vary, but it should be correct. Okay. So Bayes' rule helps doctors update the probability of a disease after observing a symptom, especially when multiple diseases share the same symptom. It combines three components. First is the prior probability, that is prevalence, how common each disease is before considering the symptoms. For example, flu is common, pneumonia is rare. Then we have likelihood, how likely the symptom is if the patient has the disease. For example, probability of fever given flu is 0.8 and probability of fever given pneumonia is 0.9. So how likely the symptom is if the patient already has the disease. So given the disease, how likely is the symptom? So this is the symptom fever and this is the disease flu. So basically probability of fever given that the patient already has the flu is 0.8 and probability of fever given that the patient already has pneumonia is 0.9. And we have posterior probability, that is the updated probability of the disease after observing the symptom. So this is the base formula. Probability of disease given symptom. Let me show you. Let me write it down for you. Probability of disease, I am denoting with D, and symptom denoting with S, is actually probability of the disease times the probability of the symptom given the disease upon probability of the symptom. So that is what's written here. So probability of disease given symptom is actually the posterior probability. That is the updated probability of the disease given the symptom. Then we have the probability symptom given disease. So this is actually the likelihood, right? So that is the probability of the system if the patient already has the disease, and probability of disease is actually the prior probability, that is prevalence of the disease. Okay, so we have this as the posterior probability, this as the likelihood, and this as the prior probability. Now this tells the doctor which disease is more likely given the patient's symptoms. So this is an example. You can see fever caused by flu versus pneumonia, right? So prior given is probability of flu and probability of pneumonia, 10% and 1%. Likelihood of fever is probability is given here. Again, this is likelihood. Observation is even though pneumonia causes fever more strongly, flu is much more common, right? According to this. And then posterior comparison, conceptually, probability of flu given fever is greater than probability of pneumonia given fever. So higher prior for flu outweighs slightly higher likelihood for pneumonia. So Bayes' rule allows doctors to combine how common a disease is, that is prior, with how strongly symptoms indicated, likelihood, and to get an updated, more accurate diagnosis, posterior. It helps differentiate between diseases that share symptoms, better clinical decisions. Now, a drug dosing agentic AI is deployed to optimize medication schedules, discuss potential unintended consequences and strategies that we can use to monitor them, and what safety measures can be incorporated to prevent unintended or harmful actions by agentic AI in hospitals. So some unintended consequences I'll discuss. The AI may give the wrong dose if the model is misaligned or poorly trained. It might ignore rare side effects or unusual patients. It may behave unpredictably when it sees new type of data, if it has not generalized well, or if it has overfitted. Then doctors may also rely too much on the AI and stop double checking. How to monitor AI? So track all those recommendations and check for unusual patterns. Keep audit logs and monitor how doctors override the AI. Use drift detectors to see if patient data changes over time. Test the AI in shadow mode before full deployment. Now, some safety measures to prevent harm. Set strict limits so the AI cannot exceed the safe dosage range, right? So some safety limit should be set, a threshold. Uh, Use human in the loop. Doctors must approve high risk dose changes, and add explainability so doctors understand why the AI made a suggestion, right? Explainability so doctors understand why AI made a suggestion. Start with a small pilot rollout and enable emergency shut off option. Now, given a highly skewed data, which measure of central tendency would you use and why? So define all the measures of central tendency, mean, median, and mode. Explain briefly how median is calculated. Explain what skewed data means here. Positive skew is right tail. So positive skew is actually right tail. This is positive skew. If this is the graph, this is positive skew, and the negative skew would be a left tail, right? Why skewness creates extreme values, and then we discuss how mean is affected by outliers, and why median is robust, that is resistant to outliers. It is stable even when extreme values exist. It represents the typical value better, and discuss the mode, but not as good as median for skewed continuous data, right? So that's it.